In this video, I will discuss the JEE Main PYQ from the topic Simple Harmonic Motion, that's SHM. First, I'll discuss some basics. SHM is the one which you are considering is a 1D motion. So 1D motion means there is only one space variable. For example, let me take a motion along the x-axis. This is the x-axis and there is a mean position. So the body will move like this. From the mean position, it will keep moving, say towards right. And after reaches some point, it will turn back. As it moves away, the velocity will keep on reducing because there is a force towards the mean position. So when it comes back here, it will have some velocity, so it will not stop here. It will go on the other side. And once it's on the other side, the force will be towards the mean position again. So the velocity will keep on reducing, and here the velocity will become 0 and turn back. So this thing will keep on continuing. So this sort of motion is called simple harmonic motion or oscillatory motion. So one example of such a motion is a simple pendulum. Another example is, suppose you have a block of mass n attached to a spring and there is a fixed support here, and from the equilibrium position or the mean position I give it a displacement like this and leave it, it will oscillate like this. So it will produce a motion like this. So for this motion, if you plot x as a function of time, so the motion will look like this. X will keep on increasing from the mean position, x will keep on increasing and then will turn back and come down towards. So this function is actually a sine function. Then only then it's called harmonic motion, simple harmonic motion. So now the next question is, what is the kind of force which produces motion? For producing motion, we need a force. So what is the kind of force which will produce this motion? So let's try a force of this type F equal to minus kx. Whether this force will produce this sort of motion. So according to Newton's second law, force is mass into acceleration. And acceleration is dv by dt, rate of change of velocity, and velocity is dx by dt. So if you use this v here, I get acceleration as d square x by dt square. So we use this thing for acceleration here. M into second derivative of x with respect to time should be equal to minus kx. So here x is a function of time, because as time changes, x will change. So you have to find this function which will satisfy this equation. So basically, you have to find a function which will differentiate it twice, will give the same function with a negative sign. Of course, there are some scaling factors are there. So the question you have to ask is, a function differentiate once f dash, differentiate twice, you get f double dash. That should be same as the function with a minus sign and some scaling factors. So if we try sine x, or here's a function of time, so sine t. If we differentiate once, I'll get cos t. If we differentiate again, I'll get minus sine t, because derivative of cos is minus sine. So for this thing, we can try a solution of this type, where x of t is sine omega t plus phi, and see whether this thing can satisfy this equation. So for this function to satisfy that equation, we should have m into, we have to put d square x by dt square for this x. So dx by dt, this derivative of sine is cos, so cos omega t plus phi is respect to time. So you have to differentiate with respect to times, this will be omega. So differentiating again, d square x by dt square. Derivative of sine is cos is minus sine, so minus sine omega t plus phi. With respect to time, I differentiate this one, so I will get omega. Already one omega is there, so it will be omega square. So this if I use here, m into d square x by dt square, that is m into minus sine omega t plus phi into omega square equal to minus kx. X is actually sine omega t. So this is same as x. So that means if m omega square equal to k, if this condition is satisfied, then the solution of this equation is of this form. So from this I get omega as square root of k by m. So once I know omega, the angular frequency, I can find the time period as time period t is 2 pi by omega, because in one time period makes one complete circle, and one complete circle is angular displacement of 2 pi. So time period is 2 pi by omega. So from this I get time period as 2 pi the 1 by m is square root of m by k. So with this basic understanding, we can solve this JEE Main question. This is the question. A mass m is attached to two springs as shown in the figure. The spring constants of two springs are k1 and k2. For the frictionless surface, the time period of oscillation of mass m is. So mass m is that there are two springs k1 and k2. So to oscillate, you have to do the equivalent positions. From this, I will displace a little bit and leave it. So once I do that, it will start oscillating like this. So to find the time period of that oscillation, you can pause and run this question. So produce oscillation from this mean position, I have to displace it a little bit. Say by an amount x. Okay, I'll take x-axis like this x-axis, the origin is here, the mean position, and positive direction is towards the right. So when I displace it slightly towards right, the spring K1 will get compressed by an amount x. So this will produce a force like this in this direction K1x. And this spring will get stretched by an amount x. So try to pull it back. So this spring will exert a force like this of magnitude K2x. But the direction of force of the two springs is towards the mean position. When I push this one, this thing will get compressed, so try to push it back. And this thing will get stretched, so try to pull it back. But both will exert the force in the same direction towards the mean position. So the restoring force acting on this block of mass m is kx1 towards left. Right direction is positive, so it's minus. Force is a vector, so you have to include the direction. In 1D problems, the direction is included in the sign. We don't need vectors, just the sign will take care of the direction. One direction is positive, other direction is negative. Right is positive. And the force of the spring K2 is K2x towards left. So direction is negative. So this is equal to minus, K1, displacement is same, minus K1 plus K2 into the displacement x. So this is like an K effective. So force is of the form F equal to minus Kx. So when an object is subject to this force, the motion is SHM if the condition K equal to m omega square is satisfied. Here K is K effective. So that means if K1 plus K2 m into omega square. So from this we get omega as K1 plus K2 by m square root. Time period of oscillation is T equal to 2 pi by omega. Omega is the angular frequency, and the time period T, the angular displacement covered is 2 pi. So time period is 2 pi by omega. So that will be 2 pi into 1 by omega, that's m divided by the full square root K1 plus K2 the full square root. So it's matches with option 3. 3 is the correct answer. So this one I explained here. So the block of mass m is displaced towards right by say amount x. So the restoring force, once it's being displaced, it's K1x and K2x in the negative x direction. So it's minus K1x and the minus K2x. So this is K1 plus K2 negative sign and to x. So it's like a K effective. So the motion is an SHM if this condition is satisfied. So from this I get time period is 2 pi by omega, and omega we can get from here as K effective by, actually I need 1 by omega, so it's m by K effective. So m by K effective and be the square root. So correct option 3.